Atomic Physics, Lecture 5, Orbital and Magnetic Quantum Numbers. Paragraph 1, Orbital and Magnetic Moments of the Electron. The second quantum number characterizing the electron wave function is the orbital quantum number. This number numbers the permissible discrete values of two interrelated quantities: the angular momentum of the electron and the magnetic moment of the electron. As is known, any rotating body is characterized not only by energy and momentum, but also by angular momentum, which is equal to the vector product of the distance from the center of rotation and momentum. The angular momentum of a body orbiting in a central field is called orbital momentum. If a rotating body has an electric charge, then it also has a magnetic moment directly proportional to the mechanical moment. The proportionality coefficient depends on the ratio of the charge of a rotating body to its mass, and is also called the gyromagnetic ratio. In the case of orbital rotation, the gyromagnetic ratio is called the orbital gyromagnetic ratio. Thus, an atomic electron has an orbital moment and a magnetic moment proportional to it. The orbital gyromagnetic ratio is determined by the ratio of the electron charge to its mass and is called the Bohr magneton. The state of the electron, that is its wave function, depends on what orbital momentum the electron has. For an atomic electron, the orbital, and therefore magnetic, moment can have not any, but only certain discrete values. It is obvious that the discrete values of the orbital and magnetic moments are pairwise proportional to each other. Therefore, both the orbital and magnetic moments are numbered by the same quantum number, the orbital quantum number. In this case, the orbital quantum number of an electron is equal to its orbital momentum measured in units of Planck's constant. Note that unlike the wave function, the energy of an electron does not depend on its orbital and magnetic moment. This is why the orbital quantum number is not used to number energy levels. Paragraph 2. Possible values of the orbital quantum number. The orbital and magnetic moments of an atomic electron can take discrete values from 0 to a certain maximum value. The maximum value is uniquely determined by the principal quantum number. This means that the magnitude of the orbital and magnetic momentum of an electron is limited by the size of its orbital. Corresponding to the orbital momentum, the orbital quantum number can also vary from 0 to a certain maximum. A zero value of the orbital quantum number naturally means that the electron has no orbital and magnetic moments. The maximum value of the orbital quantum number is equal to the principal quantum number minus 1. Thus, for orbitals with a principal quantum number of 1, the maximum orbital quantum number is 0. This means that in its ground state, a hydrogen-like atom cannot have orbital and magnetic moments. For orbitals with a principal quantum number of 2, the maximum orbital quantum number is 1. And with the principal quantum number 3, it is equal to 2, etc. As can be seen, in an orbital with a principal quantum number of 1, an electron, instead of a set of possible orbital moments, can have only one orbital momentum value equal to 0. In orbitals with a principal quantum number of 2, an electron can have two orbital momentum values, 0 and 1, etc., for each value of the principal quantum number. Obviously, the larger the principal quantum number of a given orbital, the more different values of the orbital momentum an electron located in it can have. Note that a magnetic moment creates a magnetic field. Therefore, a hydrogen-like atom will create a magnetic field around itself if its electron is in an excited state with a non-zero orbital and therefore magnetic moment. In the ground state, the atom cannot have a magnetic field since the magnetic and orbital moment in the state is 0. Paragraph 3. Types of orbitals depending on orbital momentum. Depending on the orbital quantum number, the orbitals are designated by the letters S, P, D, F, etc. That is, an orbital with orbital number 1 is denoted by the letter S and is called an S orbital. An orbital with orbital number 2 is denoted by the letter P and is called a p orbital. An orbital with orbital number 3 is designated by the letter D and is called a d orbital, etc. While distance from the nucleus determines the size of the orbital, orbital momentum determines the shape of the orbital. If an electron has no orbital momentum, the orbital quantum number is 0, then the probability distribution of finding an electron in an atom turns out to be spherically symmetric. Therefore, the s orbital has the shape of a sphere. In the presence of orbital momentum, the shape of the orbital will no longer be spherically symmetrical. So, if the orbital momentum is 1, then the corresponding p orbital has the shape of a figure 8, or dumbbell. The orbital number corresponds to the number of the Broglie waves of the electron that fit in a given orbital. So, 1 wave fits in the s orbital, 2 waves in the p orbital, 3 in the d orbital, etc. Paragraph 4. Directions of orbital and magnetic moments. The orbital and magnetic moments are vectors, so they have 2 components, magnitude and direction. That is, an electron in an atom is characterized not only by the values of the orbital and magnetic moments, but also their direction. In this case, the directions of the orbital and magnetic moments are always opposite of each other since the electron has a negative charge. The directions of the orbital and magnetic moment are usually characterized by the magnitudes of their projections onto some arbitrarily chosen coordinate axis. Ordinary spatial vectors have 3 projections, 1 on each coordinate axis. In this case, only 2 projections are independent and the third can be found using the Pythagorean theorem, knowing the length of the vector. In the case of quantum vectors, the situation is different. Due to the action of the quantum mechanical uncertainty principle, the projections of the quantum vector are determined accurate to Planck's constant. Moreover, the more definite one of the projections is, the less definite the other 2 projections are. Therefore, if one of the projections on any selected axis is known exactly, then the other 2 will be completely unknown. The uncertainty of the other 2 projections means that the projection of the vector onto a plane perpendicular to the selected axis has the form of a circle. That is, the vector precesses around the selected axis. From the above, it follows that we can determine only one of the projections of the orbital and magnetic momentum vector. The projections of the orbital and magnetic moment onto 2 other coordinate axes perpendicular to the chosen one are uncertain. The orbital and magnetic momentum vector precesses around the chosen axis. Paragraph 5. Discreteness of the directions of the orbital and magnetic moments. The direction of the orbital and magnetic moment of the electron, as well as its magnitude, can have not any, but only discrete values. Consequently, the set of possible projection values will also be discrete. In this case, the minimum possible value of the projection is equal to the value, length, of the moment vector taken with a minus sign. This value corresponds to the orientation of the moment vector in the direction opposite to the selected axis. Paragraph 6. Magnetic quantum number. The set of admissible orbital and magnetic projections is numbered by the magnetic quantum number included in the electron wave function. Thus, the magnetic quantum number characterizes the spatial orientation of the orbital and magnetic moment. and therefore the orientation of the electron orbital. Although the state of an electron, in particular its orbital, depends on the magnetic quantum number, the energy does not depend on this number. Possible values of the magnetic quantum number depend on the orbital quantum number and vary from minimum to maximum values. In this case, the minimum value is equal to the orbital quantum number taken with a minus sign, and the maximum value is equal to the orbital quantum number taken with a plus sign. Note that the name magnetic quantum number is due to the fact that by setting the direction of the magnetic moment of the electron, it thereby determines the magnetic properties of the atom and the behavior of the atom in an external magnetic field. Thus, the orbital and magnetic quantum numbers characterize the vector of the orbital and magnetic momentum of the electron. In this case, the orbital number characterizes the length of the vector, and the magnetic number characterizes its direction. Neither the orbital nor the magnetic quantum number is included in the expression for the electron energy. Physically, this means that the energy does not depend on either magnitudes or the directions of the vectors of the orbital and magnetic moments of the electron.